Our final set of concepts involves mass moments of inertia. These arise in constructing rotational dynamics equations for rigid bodies. A couple of additional points need to be made here. First, each inertia component should contain an additional subscript, referring to the origin of the coordinate system in question. If we call the origin in this slide O, then we really should define these terms as IOX, IOY, IOZ, etc., because the numerical values we get for each of these will absolutely depend on where we define the origin. Second, the terms are defined by summing or integrating over mass, but we don't actually evaluate an integral over mass. We evaluate integrals over spatial dimensions, so a key part of any evaluation is the conversion of a mass increment to a volume increment through dm mass increment equals local mass density times a volume increment dv. This means our mass moments are evaluated as three-dimensional integrals. Note that, like our area moments, there is a distance squared in the integrands of the mass moments, and the distance is the perpendicular distance from the mass increment dm to the axis in question. Mass moments of inertia must always be positive. We also have mass products of inertia, and like area products, these are not guaranteed to be positive. As with area moments, we will just focus on mass moments and leave the evaluation of mass products of inertia to another time. Governing equations for rigid body motion are obtained by representing the body as an assembly of particles, each of which is governed by Newton's second law. If we sum all these governing equations together, we get the translational dynamics equation for the body, which looks remarkably similar to the particle dynamics equation. Here, the only difference between particle dynamics and rigid body translational dynamics is that the acceleration on the right-hand side refers specifically to the acceleration of the body's center of gravity. Unfortunately, rigid body rotational dynamics equations are not so simple. If we choose the body's center of gravity as a reference point, establish a relative position vector for each particle from the center of gravity to the particle, cross that relative position vector into Newton's second law for the particle, and sum all these equations over the whole body, we get a set of governing equations that include the mass moments and mass products of inertia. The general three-dimensional set of governing rotational dynamics equations is quite complicated. The moments and products of inertia can be related to other physical quantities in a very compact way as follows. Where hg is the body's angular momentum vector about its center of gravity, omega is the body's angular velocity vector, and the quantity ig is called the inertia tensor, the components of which contain the mass moments and mass products of inertia. Written in component form, this equation looks like the following. The way we evaluate this right-hand side in component form is by taking each row in this array and multiplying it by this column. So for instance, our first equation would be hgx equals igx omega x minus igxy omega y minus igxz omega z. And we would have a similar construction for hgy and hgz. From this form, we see that the various mass moments and mass products of inertia are all components of a single entity, which we call a tensor. More precisely, the inertia tensor is a symmetric tensor of second order. We say that it's symmetric because the off-diagonal components above and below the diagonal are mirror images of one another. We say that it's second order because it forms a 2x2 array. In fact, we've run across tensors before. A scalar is a tensor of order 0, and a vector is a tensor of order 1. This is our first exposure to a tensor of order 2. Tensors obey certain transformation properties. In particular, it is always possible to find an orientation of xyz axes, we'll call them the primed axes x prime, y prime, z prime, such that the products of inertia go to 0, leaving just the mass moments of inertia. The relationship between angular momentum and angular velocity in this case becomes The components along the diagonal in the primed xyz coordinate system are called the principal mass moments of inertia. The rotational dynamics equations along the principal axes can be written. In these equations, the first term on the right-hand side includes the mass moments times the time rate of change of angular velocity, which are angular accelerations. We'll get to the significance of this second set of terms shortly. If the principal mass moments are all equal, then the governing equations reduce to a form that looks analogous to our translational dynamics equations. This provides a basis for our interpretation of a mass moment as a measure of the resistance a body offers to acquiring angular motion. Note the difference between our translational equations and our general rotational equations. If we push something in the x direction, we expect it to acquire motion in the x direction. If we push it in the y direction, we expect it to acquire motion in the y direction, and similar for the z direction. We don't ever expect to find a situation where we push something along x and it acquires motion in y. And yet, if you look at our general rotational dynamics equations, we have two sets of terms on the right-hand side. The first set of terms, the Ig omega dots, which are Ig alphas, are analogous to our translational terms. We apply a moment along the x prime direction, we get rotation in the x prime direction. The second set of terms give us coupling between different directions. What this says is that if I apply a moment in the x prime direction, not only will I get rotation in the x prime direction, but that will generally induce rotation in the other two directions. This makes the rotational dynamics equations generally very different from our translational dynamics equations. For real complex structures, the principal moments will most certainly not be equal, and the governing equations are complicated. They are coupled, and moments applied along one axis result in rotational motion not just along that axis, but along other axes as well. Because of the complexity of 3D rigid body motion, the follow-on mechanics course in dynamics goes no further than 2D rigid body motion, where there are two translational dynamics equations and just one rotational dynamics equation in the out-of-plane direction. Discussion of full three-dimensional rigid body dynamics is reserved for an upper-level class, advanced dynamics. In any event, our concern will be limited to the evaluation of the mass moments Ix, Iy, and Iz. We will not concern ourselves with the product moments. Mass moments are always positive and have units of mass times length squared. Like area moments, mass moments are always smallest about axes that pass through the center of mass of an object. There is an analogous parallel axis theorem for mass moments that permit us to relate the moments about an arbitrary set of coordinate axes to a parallel set of axes through the center of mass. We'll get to that shortly. Also, like area moments, we can define a radius of gyration, which you can again think of as a center of mass like quantity. The difference again being the presence of an argument squared instead of a linear argument as in the center of mass definition. Our parallel axis theorem for mass moments takes the following form. As with area moments, the structure of these relationships proves that mass moments are minimized about axes through the center of mass, since the d squared m offset is inherently positive and can only go to zero when the xyz axes and center of mass axes become coincident. One difference between the area and mass parallel axis theorems is in the evaluation of the d squared terms. Because the mass moment is a 3D entity, each d squared term is generally a two-dimensional distance. From the figure in this slide, we can see the following. If we define the distances xg, yg, and zg as the distance from the origin O to the center of mass of the object in question, then dx squared is yg squared plus zg squared dy squared is xg squared plus zg squared, and dz squared is yg squared plus xg squared.